Previously, when we introduced ourselves to finding the area inside a polar curve, we saw that we were integrating effectively the sum of a whole bunch of sectors, right? So we're just pretty much adding up all these sectors inside this region, inside the polar curve, and we do so by just integrating the area of each individual sector, which is 1/2 r squared, and we replace the theta with d theta. You can watch my previous video on this as I broke this down. But the trickiest part for a lot of students when doing these problems is trying to figure out exactly what are we integrating from? What are our bounds of integration here? What are our bounds of integration? Where do we start and where do we finish? And I think that's difficult a lot of times for students because they have a kind of a shaky understanding of how polar functions work and how these graphs are formed. So I want to spend some time actually talking about finding what we call the interval of integration. Or in other words, what are our bounds of integration? So let's start it with this problem here. And before we start, I'm going to encourage you to have your graphing calculator in front of you. It's again another pretty heavy graphing calculator lesson, so I'm going to try my best to explain this over this recorded lesson. But we're going to go ahead and we're going to find the area of the inner loop of r is equal to 3 minus 6 sine theta. Now, before you go ahead and start graphing this, a couple things that you want to make sure that you do. First, you want to make sure that your mode is in polar, that you're in the fifth row, you're going to switch your function over to polar. And you also, and this part is going to be a little bit different. Normally, I would have you graph the function in radians, but I'm actually going to have you graph this just temporarily in degrees. And the reason why I recommend degrees, and I'll come back to this later, is that it's often easier for us to trace and identify values in degrees. When we are in radians, most graphing calculators have a hard time giving us our values in terms of pi, which is the way we're used to understanding radian measures. Instead, it's going to give you decimal values like 0.1415, for example, and it's going to take some time for us to think about, wait, what is that value in terms of pi? So I often recommend that a nice easy workaround is just to graph your function in degrees first. So switch your calculator into degrees. And what that means is in your window, and I've screenshotted that here for you, in your window, you're going to need to adjust a couple of things. You want your graph to be graph from 0 to 360 degrees. You want your step to be 5 degrees. And what that just means is going to evaluate your polar function every 5 degrees. And I have just a kind of a tentative placement for our x min and our x max, but you can go ahead and adjust that as soon as you graph it by just hitting zoom square or zoom fit, whichever one works for you. So once that is all set, and if you hit the graph button, then you should get something that looks like this. And this isn't a great sketch of it, but hopefully it'll just kind of help give us some understanding of what's happening here. And let me actually just move that down. All right, so you should get something like that. So what I'm effectively asking you is to find the area inside this first loop, this inner loop here. So we're going to find the area inside this loop. So we know the area formula already for using sectors. But the question then is, where does this loop start and end? Well, I'm going to have you now hit the trace button. So go ahead and hit the trace button. Go ahead and hit the trace button. And if you do so, you'll notice that you'll immediately get, and I'll just do this here, mark this, you'll get your little cursor or your blinker starting here. This is when theta is equal to 0, both 0 degrees and 0 radians. It starts there. So your graph doesn't actually start at the pole, which might surprise some students. And then if you continue now to hit the right arrow key, hit your right arrow key on your calculator, and by the way, I'm describing this using a TI-84 Plus, and my directions should work for most TI calculators. If you have a Casio, I would just suggest that you kind of Google it on your own and try to find a way of working using a Casio. Sorry, I just don't own a Casio. So if you hit the right arrow key, you're going to notice that your cursor is going to start to move to the left or counterclockwise. And when it ends here, or when it gets to this point right over here, it should tell you that your theta value here, theta is equal to 30 degrees or pi over 6 radians. Again, if you were in radians right now, it would give you a decimal approximation for pi over 6, which might be hard for us to kind of grasp as to what exactly that value is. So instead, it's easier just to write within degrees, at least for now. So this is going to be 30 degrees. So what's going to happen, again, if you continue to hit the right arrow key on your calculator, this cursor is now going to start to move, again, counterclockwise around this loop, and it's going to come all the way back around. And then once it loops all the way back around and it closes this inner loop, that now is going to close at theta is equal to, and hopefully you get 150 degrees, or 5 pi over 6. So this trace feature allows us to find our bounds of our integration here. We should notice that theta is equal to 0 at, excuse me, not theta is equal to 0, r is equal to 0, I apologize, at theta is equal to pi over 6, 5 pi over 6. Okay, so it starts the loop at 30 degrees and closes the loop at 150 degrees. Now, students might often ask, wait, so that's cool and all that I can use my calculator, but is there a way for me to do that by hand? And there absolutely is. So just think about this. If I wanted to actually do this by hand and I wanted to find those intervals of integration, which I honestly recommend, most of the time you should be doing this. Ask yourself, well, I know my loop starts and ends at the pole. Well, what do we know about the pole? What is the R value at the pole? So at the pole, my R value is equal to 0. So what that means is you want to take this polar function then and just set it equal to 0. 0 is equal to then 3 minus 6 sine theta. And just by simplifying sine theta, we should see is equal to 1/2. And algebraically, we can just find that theta then is equal to pi over 6 and 5 pi over 6. So it's good to know both. It's good to know how to graph this by hand, but also how to use your calculator to find those points of intersection and therefore our bound or our bounds of integration. So speaking of integration, let's go ahead and let's do the integral first, and then just make sure that we understand visually what's happening or graphically what's happening as we're integrating. So we know that the area is going to be the following. It is the integral from pi over 6 to 5 pi over 6, 1/2, and I'm just going to write this out first, and I'm going to mention a couple things that you can do with your calculator just to make sure that you get the correct answer. Our R function, or our function, squared d theta. Now, before I calculate this, I'm going to pause and mention a couple things. Now, while I used my calculator or had my calculator in degrees so that I could find my interval of integration, when you are integrating using your calculator, you want to make sure that you are in radians. I want to write that, integrate in radians. And this is because when we are integrating with respect to theta. And when we are doing calculus with angles, we want to make sure that we're integrating in radians. So really the only reason we switched to degrees here was so that we could easily trace these values. And if you found the intervals of integration by hand, like I did up there, then honestly, you could just do the whole thing in radians. And so you don't have to worry about switching back and forth. So many students find it's often faster to work that way. But we're going to integrate this in radians. That's why I had my interval of integration be pi over 6 and 5 pi over 6, not 30 and 150. If you try to integrate it in degrees, you won't get the correct answer. Another thing that I want to just emphasize here is that when you are integrating this using your calculator, you could obviously just write out the function again. But if you then hit in your calculator instead, hit the alpha button, oh, I can't spell that, alpha, and then hit the trace button. And then what you can then select is R1. And then R1 is effectively what you just entered in for your graph. And so this here would just look like R1, and then you can just square that. And I often prefer doing that when I'm doing my calculator for two reasons. One, it's a little bit faster. I can save the time of having to type everything in again. And two, it prevents the possibility that you might accidentally type something in incorrectly, like leave off a theta or leave off a negative sign and end up getting the incorrect value. So that's a suggestion there as well. So when you go ahead and integrate, I believe you should get for this one, and let me just go ahead and integrate that myself. So I want to say from pi over 6 to 5 pi over 6. And actually, before I continue, I want to make sure that I'm back in radians. And I was not, so that's a good catch. And then from here, I'm going to go ahead and do 0.5 alpha trace. And you can't see what I'm putting in right now. I apologize. D theta. And you should come out 2. And this is an approximation 4.892 if you're rounding, 1 if you're truncating, but this should be your approximate area inside this inner loop here. So now that I've integrated this using our calculator, I want to make sure visually and graphically you understand what's happening here. Starting with theta is equal to 30 degrees or pi over 6, depending on if you're in degrees or radians. As theta increases and we start moving counterclockwise, what's happening is these sectors, that little red line that I've just drawn, you can kind of visualize that as a very thin sector. And as theta increases, what's happening, and I'm kind of over exaggerating this right now and spacing it out further so it doesn't really look squished, but what's happening is I'm really drawing an infinite number of these really thin sectors where it starts from the pole, this part's important, from the pole to your R value, to the edge of that curve from that R value. So you can almost imagine that I'm kind of fanning out and creating this shaded in region that way. And that's important because sometimes students will make the mistake of actually trying to start drawing these sectors from where theta is equal to 0. And I know that sounds like a subtle difference, but you'll notice that in this problem, theta equals 0 is actually this point over here. So sometimes students will start drawing their sectors out this way, which would be incorrect. You don't want to do this, right? That's not how the polar function is formed. So I just wanted to clarify that and make sure we don't make that kind of mistake. So to kind of answer the question of how would we shade in or identify the shaded region, if I said find the area above the x-axis, enclosed in this region here, well, you would start from the pole and you would go out to where theta is equal to 0. And then as theta increases, this region, you would integrate it. In this case, the bounds of integration would be from 0 to pi over 6. That would give me this shaded region here. And if you wanted to, you could identify that this region here is symmetric over the y-axis, so it's going to be congruent to this region that I've just highlighted. So once you find the area of that region to the right, you could just double that to find the region's area to the left. Okay? So let's go ahead and let's try one more example. It's one of the examples from the notes here. So let's find the area inside the loop of this function here, cosine 2 theta. Now, I went ahead and I've already sketched the graph for you, but I encourage you to pause right now first and sketch this for yourself. You may want to switch back into degrees. You don't have to, but you may want to. And if you sketch that out, you should get a rose petal curve that looks like this. Now, first off, if I want to find the intervals of integration, I could do this one actually pretty easily by hand. I may not need a calculator. You may want to check both ways since you're just starting off and you want to practice this. But I notice that my interval of integration, well, I know that one of my loops here is going to be at 0, okay, when r is equal to 0. I know that one of my loops here, and by the way, I'm just talking about one of my loops is the following, something like this. I know that at least the starting or the ending point of my loop is going to be when r is equal to 0, So let me solve. So when r is equal to 0, 0 is equal to cosine of 2 theta. We've got a double angle here that we're going to solve for, right? So when is cosine equal to 0? When this angle here is equal to pi over 2. So 2 theta is equal to pi over 2. And actually, there are a number of angles where cosine is going to be equal to 0. So we would say pi over 2 and every pi multiples of every pi multiples or apart, I should say, between pi over 2. And so if we go ahead and divide everything by 2 here, theta is equal to pi over 4 plus pi over 2n. So these are the angles that are going to cause cosine of 2 theta to be equal to 0. So we know that at least when theta is equal to pi over 4, we have this point here. We're going to be at the pole. And every pi over 2 units apart is when we hit that pole again. We're going to go back to the origin every pi over 2. Now, let's just maybe look at this graphically because that might help a number of students. If you, again, graph this in degrees and hit the trace feature, your blinker is going to start right here. This is where theta is equal to 0. And as you hit the right arrow key on your calculator, your cursor is going to move counterclockwise until it gets to this point over here at pi over 4. And then it's going to continue to move around counterclockwise, and it actually is going to move down below the y-axis, and it's going to loop back around. And when it loops back around, it's going to hit the pole again here. I'll try to see if I can draw this. It's going to hit it here, back here at theta is equal to, can you figure out where it would be? You guessed it. This would have to be at 3 pi over 4 because it was pi over 2 radians away from pi over 4. We figured that out by seeing this here. So we actually have a number of different approaches for how to actually graph this problem. If I wanted to, I could have stated that I'm going to start from 0 and I'm going to graph this all the way over until it hits pi over 4. In other words, this pedal here, if I draw these here, starting from 0 to pi over 4, from 0 to pi over 4, I can find the area of this as such. So I would say, I may actually also do this, and this will hopefully make sense in a second. So to find the area of this entire pedal, I am going to do 2 times the area of half the pedal, which is 1/2 the integral from 0 to pi over 4 r squared, so cosine of 2 theta squared d theta. So again, what I've just found here is the area of half that pedal from 0 to pi over 4. I just went ahead and I integrated that from 0 to pi over 4. That's going to give me the area of half of that pedal. So that just means I'm going to double it. That 2 is going to divide out with that 1/2. And so you're just integrating really this. And so when you put that into your calculator, you should find that your approximate value, again, make sure you switch back to radians if you're using a calculator, but your approximate value is 0.392699. So let's just say 3 to round. And what is the exact value of this? Well, it's going to be pi over 8. And how did I figure out it was pi over 8? Well, I didn't show it, but look at that function that you have up there. That's something that you should be able to integrate by hand at this point. I'm not going to do that right now just for the sake of time, but hopefully you can pause and make sure you check to see that you do indeed get pi over 8. Now, some of you may be thinking, well, Mr. No, could I just have integrated this from pi over 4? From pi over 4 to pi over 8? In other words, find the area of the pedal with those bounds of integration? And absolutely. So that would just be the following. The area would just be 1/2, I'm just moving the constant to the outside, from pi over 4 to 3 pi, did I say pi over 8? I can't remember now. 3 pi over 4 and cosine of 2 theta, that entire function squared d theta, and that should give you the same exact thing. So you do have some flexibility with what intervals you use because we have a rose petal curve, which has 4 congruent rose petals. So as long as you understand how this function is formed and how this is graphed, then you do have a bit of flexibility there with which intervals you choose.